Hello and welcome to this first ad hoc lecture, recorded lecture in the course Algorithmic Problem Solving. So the content or the purpose of today's lecture is to talk about strings. Actually, we will have a few lectures talking about strings. So in this first lecture, we're interested in two different problems. One is tries, how to basically represent all the prefixes of a string. And secondly, how to do string matching and how to do multi-string matching. So first, some initial terminology. We're in this lecture, we will talk a lot about suffixes and prefixes. So a suffix is a substring that occurs at the end of a word, and a prefix is a substring that occurs at the beginning of a word. So if we have the word banana, the suffixes are a, na, ana, nana, annaa, and sometimes the whole word banana as well. And the prefixes are b, ba, ban, bana, banan, and sometimes the full word. So that's pretty basic. Now we come to the first and actually very useful data structure, which is called trie or prefix tree. So basically what we're doing here is that we're building an ordered tree for storing a set of data, usually strings, that are optimized for doing prefix searches. So basically we want to find all the words where all the words have a common prefix. For example, does any word in the set start with a prefix mart? And basically the general idea is that you have a 26ary tree. So basically, for every possible letter in the word, you have a branch from the root. So basically, all words that start with that letter, they branch into that part of the tree. So in this case, we have the word 8. So it means that we start with an A, continues with a T, and then an E. We have out, O-U-T, but we also have one. And so here we see that one and out, they share the same starting letter. So therefore, we have this. And we can also see here that if we have a black dot, that means that we have a word ending in that. So in this case, we have a, at, and 8. So actually we have 3 different words represented by a single branch. Here we have on and one, but we also have out. So in this branch, we have 2 different words. Here we have my, me, and mud. So actually we have three different words here. So basically, it's really simple to build this kind of data structure. So basically, you always start with an empty tree, and then you add the words one by one. And basically, you start in the root, and you check the first letter. If there already is a branch for that letter, say for example we want to add ape, we see that it starts with an A. And then we see that the second letter is a P, and then there is no branch for P. So that means we would add a new branch for P, and since we just basically add all the remaining words, so we get ape. So actually it's very easy to build this data structure. And to find all the words that start with a certain prefix, we basically just check. So for example, if we want to check all the words that start with M, with the prefix M, then we would follow the branch M here, and then we would basically look what are all the words that are below this point in the tree. In this case, it would be me, mud, and my. So this is a very nice and useful data structure. So what can you do with this? Well, you can use it, for example, to build a dictionary. So you want to find words. You can use it for autocomplete. So for example, on the good old times when we had the T9 autocomplete system, was basically based on this kind of approach. We can also do the longest prefix matching, so basically see how far down the tree can we get to match the prefix. We can do spell checking to find words that are close, and we can also do substring matching. So this is a very nice and useful data structure. Then we have the string matching problem. So in the string matching problem, we have a text called S, and then we want to find all the occurrences or particular pattern P in this text. So to do this, it's important to notice that each substring is a prefix of the suffix. So it means that, if we can extend, what it means that this substring is a prefix of suffix means that you can extend this string with a few more elements. So that means that we can use this in order to use a trie to solve the string matching problem. So we build a trie of all suffixes of the string. So we basically take all the endings of the original string and build a trie based on that. And this will take the order of the length of the string, squared. And then to find all the occurrences of P, we basically just look in the trie, and we can just match the prefix. So this is linear in the length of the pattern. The good thing here is that if they have the same text that is being used multiple times, then we can reuse the trie that we built for many queries. But of course, it's still quite expensive being quadratic in the length of the text that we want to search, which of course can be quite long. So therefore, there are more efficient solutions. There is the built-in string library of your favorite language, or you can implement one yourself, namely the Knut-Morris-Pratt, which you will do in Lab 3.1. So I will provide a link to a video presenting, or actually two different videos presenting Knut-Morris-Pratt algorithm if you want to hear me, or if you want to hear someone present it rather than just read the implementation. So this is a quite remarkable algorithm in the sense that it's linear in the sum of the length of the original text and the pattern, and that you only need to store as much space as you have the length of the pattern. There's also an alternative string matching algorithm called Boyer-Moore, which has the same time and space complexity, but it is slightly more efficient than the Knut-Morris-Pratt when the alphabet is large. So then we have the third problem that we're interested in this lecture, and that's the string multi-matching problem. So in this case, we have a single text and multiple patterns, and we want to find all the occurrences of all these different patterns in the text. So here there are two good approaches. The one that you will be implementing in Lab 3.2 is called the Aho-Korasik algorithm, and this basically provides a solution that is linear in the size of the text, plus the size of each of the pattern, plus k, where k is the total number of matches. And there is actually an even more efficient approach that you can do by implementing a suffix array, but that we save for next week. Thank you very much. So, well, I guess I wasn't really finished. So basically in this lecture, we have presented the tree data structure. We have then used the tree data structure to solve the substring problem. We have mentioned the Knut-Morris-Pratt and the Boyer-Moore algorithm for substring matching, and the Aho-Korasik method for doing multiple string matching. And we also mentioned the suffix array that we will talk more about next week. Okay, now I'm really done. Thank you.